Swayam Prabha. Digital India. Educated India.
Good morning to one and all present here. I take great pleasure in welcoming our first lecturer for today, Dr. T.E. Venkata Balaji. Working as an associate professor in the Department of Maths in IIT Madras, Dr. Venkata Balaji's current research interests include algebraic and complex geometry and their interactions with analysis, topology, and algebra, as well as he's interested in moduli spaces. We welcome you, sir. Looking forward to your lecture.
Yeah, thank you. Thank you for for waiting. I mean, we are all, quite tech savvy, and there are always glitches with the tech. So, are you able to? Is audio okay? Fine. Any problem? Should I talk louder? So, all right. Thank you for waiting. So, what I have been thinking of is, to tell you about, certain aspects of geometry which are connected with just curves on the plane. So they are called plane curves, okay? And of course, many plane curves, the simplest being the straight line, and then you have the circle. Then of course, you have, come across conics, okay? Conic sections as they are called, which are essentially sections of a cone, a right circular cone by a plane, okay? And they give you the, various cases which are the parabola, the ellipse, the hyperbola, and as special degenerate cases, you will also get a pair of straight lines, a double line, and a single point also. Okay, so these are conics, and then you have more complicated curves on the plane, and all these examples that I gave you, they are all algebraic in the sense that they can be written as algebraic equations. They can be written as zeros of algebraic polynomials. So a circle centered at the origin, radius let us say r is x squared plus y squared equal to r squared. That is the equation of the locus. And you see this is a polynomial in of degree 2 in two variables. Okay, and similarly you have general equation of a conic is a general equation. Is given by a polynomial of degree 2 in two variables, okay, and there is a certain determinant condition that will ensure that it is a conic, okay. So these are all equations which are algebraic in nature, and the loci in the plane, namely the points which satisfy these equations, they are going to be algebraic curves basically, right? So straight line, circle, conics, they are all examples of algebraic curves. But you can have also what are called as transcendental curves. Transcendental curves are curves for which the function is a transcendental function. That means it's not algebraic. Okay, and you can have many. So the simplest example, for example, you can look at sine function. Okay, or you can look at exponential function, or you can look at the logarithmic function and look at the curves corresponding to those. So you can have highly non-algebraic equations. So these are various types of curves on the plane, and what I am going to do is I want to tell you about transforming curves. Okay, so maybe I will use a little thicker. So the first thing I want to tell you is something that's very, very interesting. Okay, and the idea is as follows. So what you do is you take some curve, okay, and you given a curve, and we'll assume that the curve is smooth, okay. That what does that mean? It means that at every point I can draw a unique tangent to the curve, okay, and I also want that these tangents should continuously change as the curve changes, okay. And so if you draw the curve, have you been exposed to calculus? Yes, okay. So you see, if you draw the graph of the curve as like this, y is equal to fx is the curve, this is the graph, okay. Then you know that at any point, if you take a point x naught comma y naught on the curve, then you know this y naught is going to be f of x naught because it will satisfy this equation, okay. Y equal to fx, the graph of this function is exactly the locus where this equation is satisfied. So if x naught comma y naught is there, then it should satisfy the equation. So y naught must be f of x naught. So this x naught comma y naught is y naught is just f x naught, and then what you do is at that point you draw the you draw the tangent to the curve at x naught, okay. And then what does calculus tell you? How do you get the slope of this line? Using calculus, it's a derivative, right? So the slope is just f dash of x naught. Okay, is a derivative. It's just dy by dx at x equal to x naught. Okay, that is the slope of the tangent. Okay, and that is just the it is actually the tangent of the angle made by the line with the positive x-axis. All right, and so once you have this tangent, you can also draw this normal. So this is a normal at x naught. Okay, so at every point you have a tangent and you have a normal, and what I want these tangents to change continuously, which means that basically the slope of the tangents should change continuously, but the slope function of the tangent is just the derivative f dash. So you want f dash to be continuous. Okay, so smooth means f dash must be continuous. Okay, and the language for this is it's called C1 smooth. C1 means first continuously differentiable. That means the first derivative exists and it is continuous. All right. So so you have this idea, and then what do you do with this? What you do is that you start doing the following thing. You start drawing normals. You at all points of the curve you start drawing normals. So what I do is I'll draw things like this. So I take this point, I'll get a normal like this, and then I take this point, I'll get a normal like this. Okay, you draw a normal at every point. Okay, so you do this, and then the question is what happens. After all, you are just drawing lots of lines. Is something going to come up? So something does come up. That's what I want to show you. So let me show you some pictures. So the interesting thing is, if you start drawing these normals, what will happen is that magically a new curve shows up. Okay, so we want to understand what that is. So let me show you some pictures. It can't be done without showing pictures. So I'll have to show you. Let's see whether it is here. Here it is. So here's the first picture. Okay. So let me explain this. So you have this. So this is the ellipse. Okay, this is the ellipse. Okay, and then what is happening is that at every point of the ellipse I am drawing a normal. Okay, so you can imagine. So if you take this point, then this is the normal. Okay, then if you take some other point, say here, this is the normal. All right, and similarly if you take this point here, then this is the normal, and so on. So at this point you have one more normal here. The normal at this end will be this one, the normal at this end will be this one, and of course the normal at this end will be this vertical line, which will also be the normal at this lower point. Okay, so all these red things that I am drawing, they are all normals. Okay, but if I draw sufficiently close normals, then you see what comes up. What comes up is this, you see this beautiful thing here. So you get this picture, you get this curve, which I am drawing in blue. Okay, you get this beautiful curve, right? And so this curve shows up when you draw the normals. Okay, and this is what is called an asteroid, but it is an asymmetrical asteroid. That is, an asteroid is usually something like this, which is symmetric about both the axes. And usually it has an equation x to the 2 by 3 plus y to the 2 by 3 is equal to a to the 2 by 3. You would have seen such examples in calculus. I don't know whether you've seen such examples. So you see, this is your asteroid, and of course, you know, these lengths will be, you know, 2a. Okay, this length will also be 2a. Okay, this is an asteroid, and what you get in this case is what is called an asymmetric asteroid. Asymmetric asteroid. Okay, because it's asymmetric in the sense that, you know, of course, it is also symmetric about both the axes. So it's not asymmetric in that sense. It's asymmetric in the sense that it's elongated in one direction, okay, and shortened in the other direction. It's like saying an ellipse is asymmetric, okay, but that's kind of a misnomer. Actually, an ellipse is, of course, symmetric about both the axes, but the point is it's asymmetric in the fact that, you know, the major axis and the minor axis, if they are different, then it's asymmetric in that sense, okay. So don't get confused with the word asymmetric, okay. It's just that it's elongated on one side. So the point is that you draw all the normals and this new curve comes up, okay. So here is one example, then here is one more. So here is another very important curve, okay, and so this curve here, so let me show it as so this is the curve, okay, which is like this. Basically, you know, you have this thing that I am drawing in red, except for that inner loop, the rest of it looks like an apple, okay, or a heart shape, and it's called a cardioid, okay, and with this inner loop, it is what is called as a limacon, okay, it's called the limacon of Pascal, and it's a beautiful curve, and of course, you know, there is this point here where it crisscrosses itself, okay, and let me remove that. So this is this curve, and again what you do is you start drawing normals to this curve, okay. So I mean, this picture is somewhat confusing. You have to look at it carefully. So you see, at this point, for example, this is the normal, okay, and you should also watch out that, you know, there are other normals you know, nearby, but they are not at that point. So you must understand that, for example, you know, if you take so let me show you something. Let me give you an example. So what I wanted to tell you is, yes, for example, you know, if you take, so let me show you another line so that you get an idea. So if you take, for example, this line, okay, this green line, this is not the normal at this point actually, but if you extend it all the way here, okay, then you see this is the normal here. It is the normal from the inner portion, okay. So you must understand that the normals, where they are coming from, you have to be careful. But you draw all these normals. Again, something amazing happens. What happens is that you get this, you know, you get this nice curve in the, you get this nice shape here. Okay, you get this beautiful curve here. And you see these curves, they just show up. You just draw the normals. You will draw sufficiently enough normals, okay, which means sufficiently close normals you will draw, and then this blue curve shows up, okay, and so, you know, this curve shows up, and what is happening we would like to understand. So here is one more example. So this is the good old you know, our good old sine curve, okay. So this is just your sine curve, okay. This is your sine curve, and again what you are doing is you are drawing normals to it at every point. So, you know, so these are the normals, you know, at every point these are the normals. So at this point this is the normal. So somehow my picture is bad. So you see, at this point this is the normal. Similarly, somewhere here, you know, this is normal, all right. So you have, so if you take the sine curve, all right, and draw the normals, then what happens is that again, you know, a new curve shows up, and what is that curve? That curve is exactly this one, namely this is the blue curve that shows up. Okay, all right. So so this is something that's happening, and you can, so let me also show you an animation about what is happening. I have stored it somewhere here. Where is it? Here it is. Yes. So yeah, so here is the case of the ellipse. You see you have the red ellipse, okay, and the blue lines are the normals which are drawn as this point moves around, and you see this very beautiful asteroid that is formed. Okay, so this is a very beautiful kind of thing that comes up. Okay, and then I can also show you some more examples. Where is this? So I have just put them here so that you can I did go somewhere. Yes. Just hold on. So let me just try to get hold of. There are too many bookmarks, and you know, and there are curvature. Here it is. Yeah. So here is the so there is this ellipse now, which is, you know, the major axis is along the y-axis. It's vertical. Okay, and then you know, the normals are drawn to that ellipse, and you know, all these normals, they you know, trace this curve, this asteroid. Okay, and but you know, there's something interesting that I want you to understand. What is happening is, you see this, so you look at this situation. You have this ellipse, okay, and on the ellipse, which is in kind of dark blue color, okay, at every point you are drawing the you know, normals. They give this pink colored curve, which is the asymmetrical asteroid. Okay, now we are so what this picture is doing is that, you know, you are now moving on, not on the ellipse, you are moving on this asteroid. Okay, and at every point as you move on the asteroid, you know, you can see the blue lines are the normals. Okay, but there's something else that's happening. There is this circle that is, you know, that's also moving, that you can see. Okay, and if you think about it, you see at every point wherever this circle is touching the ellipse, okay, that is the kind of the best fitting circle at that point. So you see, at the extreme ends of the ellipse, you see the circle becomes very small, and when you go to the you know, these flatter sides, the circle becomes very large. Okay, and again when you come to this top portion, the circle becomes very small. Again it starts becoming bigger, and then it becomes, you know, biggest, and then it becomes smaller. So you see, what is happening is that if you look at this picture, you see what is happening is there are two things that are happening. As you if you look at the ellipse, there is a circle touching the ellipse. Okay, and it is the best fitting circle to an ellipse. Okay, so let me write that down. See, so what we are doing is, see, you have a curve like this. Let us say, suppose you have a curve like this. Okay, and you see, suppose I take a point. All right, then what I do is, at that point, of course, you know, I have tangent. Okay, then at that point I have the normal. Okay, and these are at 90 degrees. All right, then what you do is that you start drawing circles touching the curve at that point. So when do you say two curves touch at a point? If they have the same tangent. Okay, so what I can do is at this point I can draw lots of tangents. You see, I can draw lots of circles tangent to this curve. So I can draw a small circle like this, or I can draw something bigger. Okay, then I can draw something much more bigger. Okay, of course I could have drawn it on the other side also. Okay, but there is one particular circle which is kind of the best fitting circle. Okay, in the sense that that circle is closest to the curve when compared to all the other circles. Okay, so that is a best fitting circle at every point, and maybe the best fitting circle, if I want to show it, let me show it in some other color, maybe blue. So the best fitting circle is going to be something like this. Okay, and of course I don't have space to draw somewhere here. Its center will be somewhere here, far away. Okay, and this best fitting circle at the point P, okay, on the curve, this circle exists and it is called the circle of curvature. At the point P, okay. And what is the meaning of best fitting? It means that among all the circles that you can draw, which are touching the curve at the point P, namely all the circles which have the same tangent as the curve at the point P, this circle is the closest to the curve. That is, if you measure the distance between the perpendicular distance, okay, the distance between this circle and the curve, that will be the least. That is going to be such a circle. Okay. Now, such a circle exists to prove that. That's a mathematical thing. Okay. You can either use calculus to prove it, or you can use geometry with a mix of calculus. Okay. So this exists. Okay. And it can be proved using some calculus. Okay. So proof uses calculus plus geometry, and in fact it uses also what is called as analysis and topology. So so of course you are all familiar with calculus. It's just differentiation integration, the simplest way. And differentiation has got to do with at least first derivative is going to give you the tangent. Okay, at least that much Higher derivatives, what do they mean? That has to be understood. Okay, and I'll come to that. It's actually the second derivative that is involved here. All right, and the second derivative has got to do with what is called as curvature. Okay, so yeah, you have a question. It's unique. When I say, yeah, it is unique. The circle of curvature is unique. Okay, and yeah. If the curve is an arc of a circle, then that circle will be the circle of curvature. If the curve is throughout an arc of a circle, okay, if it's a portion of a circle, then the circle of curvature will be that circle. Okay, if it is not a circle, then you can find a unique circle. And the important thing is that how big or small that circle is depends on how much the curve is curving. So if you have a curve which is sharply curving like this, let's say, okay, and you take this point, you see at this point, the circle of curvature is this small. Okay, whereas if you, so this is what is happening in the ellipse. If you take a point like this, you see the circle of curvature will become very large. Okay, so the point, where the point is being considered, that is also important. As you change the point, the circle will change its shape depending on how much the curve is curving or not curving. Okay, so if the curve is curving more, you can imagine the circle is smaller. If the curve is curving less, then the circle must be larger. Okay, so if you take an ellipse, for example, at the major axis, you see it's curving maximum. So you have small circles, and at the minor axis it's curving minimum. So you have large circles. Okay, and you can see that already you have some idea of curvature. You see, the larger the curvature, the larger the curve turns. Okay, you can see that the circle becomes smaller. Okay, and if you want curvature to mean that it should measure how much the curve is turning. Okay, then if the curve is turning a lot, then your curvature should be more. Okay, and if it is turning less, the curvature must be less. So what does this tell you? This tells you that if the curve turns more, okay, the curvature must be more, but in that case the circle becomes smaller. And if the curve turns less, okay, then the curvature is less and the circle is larger. Okay, so you see the size of the circle and the curvature are inversely proportional. And what is unique about a circle is its radius, right? Circle is essentially given by its radius. So what you do is that the size of the circle is directly proportional to the size of its radius, and the curvature is supposed to be inversely proportional to the size of the circle. Therefore, what is the natural definition? The curvature is just reciprocal of the radius. Okay, so what happens is that at every point you get this unique circle called the circle of curvature. Okay, at that point, and you get, for that point you get what is called as the center of curvature. Okay, and then this circle will have a radius. So if you go put this normal will pass through this, and you get this r. Okay, this is this is called the radius of curvature. So I will be very careful and write RP is radius of curvature at P, and I will put center of curvature C of P. Okay, and the circle of curvature I will call it as C sub P. And this P is important because as P changes, everything will change. The circle will change, its radius will therefore change, center will also change. Okay, and what you should notice is that the curvature is actually by definition 1 by the radius of curvature at P. Okay, and this agrees with everything that you physically see. For example, if you take a circle, okay, if you take a circle, at every point on the circle, the best fitting circle is just that circle, right? And therefore the radius of curvature will be just the radius of that circle. The curvature will be just reciprocal of the radius of the circle, and as you change the point, the circle doesn't change. Okay, because it's the same circle. Therefore, on a circle, the curvature is constant, and the curvature is just the reciprocal of the radius of curvature, which is just the radius of the circle. All right, and you can see if the circle becomes smaller, then its radius becomes smaller, so the curvature becomes larger, which is correct because a smaller circle turns more, a larger circle turns less. If you take a larger circle, then its curvature is going to be the reciprocal of its radius, which is larger, so it's going to be smaller. And you can take the limiting case when the radius goes to infinity, and what do you get? You will get zero curvature, and that's a straight line. A straight line can be taken as the case of a circle with infinite radius. Okay, so you take a circle and then you start moving the point to infinity on the plane. Then this circle will become more and more flatter, and in the limit you will get a straight line. So a straight line has zero curvature. So you see, this definition of curvature is very nice. Straight line has zero curvature, circle has constant curvature, and you have this idea of curvature. And what is happening is that the existence of this unique circle called the circle of curvature, that involves some work. Okay, so it involves calculus, which anyway differentiation. The integration is just idea of summing up. Okay, for example, integral under a curve is just the area under the curve. That's just put it in very easy language. And when I say geometry, See, geometry is that you mix up things that you see physically and then you want to prove those things. And the geometry uses everything. It uses calculus, it uses analysis, it uses topology. What is analysis? Analysis is got to do with limiting processes. Okay. So, for example, whenever you take a limit, you are in the situation of analysis. All right. For example, calculus is coming from analysis because you are taking, when you do derivatives, you are taking limits of difference quotients, and therefore it is a limit. So, it is also involves analysis. Integration is also a limit. It's just a limit of Riemann sums. Okay. You are just trying to approximate area under a curve. Okay. So, that is also a limiting process. Integration is a limiting process, differentiation is a limiting process, and the limiting processes are in general studied in analysis. And what is topology? Topology is, to say it in very simple words, it's a science of position versus continuity. How is position connected with continuity? Okay. So, if you want to generalize it, that's what gives rise to topology. And all these subjects are used to prove, the existence of circle of curvature. Okay. So, you can find the circle of curvature, you can find formulas for that, you can find the radius of curvature and formulas for that, and so on and so forth. Okay. Now, you see, now I want you to look at this picture. Look at this curve. At the point P, I have the normal. That normal goes and hits the center of curvature. Okay. All right. Now, here is the interesting thing. In all the pictures that we saw, okay, the new curve that you are getting is actually the locus of the centers of curvature. Okay. So, this locus of centers of curvature this is what is called as the evolute of the curve. Okay. The locus of centers of curvature of a curve. Okay. So, you must understand that as the point moves on the curve, okay, the circles of curvature are also changing, their radii are changing, the centers of curvature are also changing. So, as you move the point on the curve, the center of curvature also moves. So, as this point on the curve traces the curve, the center of curvature also traces the curve, traces a curve, and that is a new curve. That is called the evolute. Okay, and that is what is happening. So, what you are seeing here. So, for example, what did I show you? So, that was the picture here. So, you see here what is happening is that in this picture what is happening is that you see this blue curve, which is the ellipse with the vertical being the major axis. Okay, its evolute is the pink curve, which is the asteroid, asymmetrical asteroid, and see these normals that are being drawn from a point on the asteroid, they are actually going to be, if you look at it very carefully, they are the radii of the corresponding circles of curvature. You just look at the picture carefully. Okay, the full normal is not drawn, only the normal from the point on the curve, which is the ellipse, to up to the radius of curvature is drawn. And actually what is happening is that it's what is moving, if you want to look at the moving point on the curve, it is actually the point of contact of that circle with the ellipse. That is a moving point on the curve. And then from that point you are drawing the normal and you are extending it up only up to the point of curvature, the center of curvature. And that point of curvature is moving, and that's what traces this pink curve. Okay. So we say that the pink curve is the evolute. This asymmetrical asteroid is the evolute of the ellipse. Okay. And then there are, so let me show you, so incidentally this, you can also access this website, it's intmath.com. So then the next thing is, let me show you what is happening with the, nephroid. A nephros is kidney, okay, so it's a kidney shaped curve, all right. And you look at this, look at this, if you take a nephroid, the big blue kidney shaped thing, okay, Then the evolute is this pink shaped nephroid, which is a smaller one, okay, and it's half the size, but it is rotated by 90 degrees. So you see, you get this very nice picture. And the nice thing is that you can see, if you remove this, you can see how the circle of curvature is changing. Okay, so you see, for the, as you can guess, at the ends it's biggest. But the interesting thing is, you see, at this point there is actually a cusp. This is called a cusp. Okay, it's called a cusp because at that point, the curve is not smooth. There is a change in the tangent, sudden change in the tangent direction. All right. So what happens is, as you go closer to the cusp, you see the curve bends so much that the circle of curvature just collapses to a point. Okay, on one side, and then again it grows from a point to become bigger. Okay, and that's how. So you should watch this carefully as this point, as a point of contact comes closer. Okay, you see that you get this circle of curvature collapsing to a point and then again becoming bigger. Okay, and that's how you get this pink portion. All right. And so this is, if you look at only the, so this circle tells you, it's just showing you the circle of curvature moving, and its center that is moving is the center of curvature, and that is what is tracing that pink curve, which is the evolute. Okay, and if you want, you can draw the normals. Okay, so you can see the normals. These are the normal lines, which are the radii from the point of contact on the curve to the center of curvature. Okay, and you get this thing, right? And of course, there you can also draw circles. You can draw all these things and you will get some cute patterns. But anyway, probably they are somewhat beautiful to look at. But anyway, you can disable that. Okay, so this is what happens. Then here is another example. So here again you have the blue curve, which is the asteroid. Okay, and you do the same business. What you get is the evolute is a bigger asteroid, but you see now this bigger asteroid is the pink one, and that is this asteroid rotated by 45 degrees and scaled double. Okay, so the pink asteroid is just the blue asteroid. You take the blue asteroid, rotate by 45 degrees, and then scale it to double. Right. So this is what happens. And here also, what you can do is that you can draw the normals. Okay. You can draw the normals, and then you see that the normals, they give you this. All right. The normals give you this. Okay, so the pink one is the evolute of the blue one, right? Then I can show you one more example. This is the example of a parabola. So in the case of a parabola, which is the blue curve, you get this pink thing. That is going to be, it's called a semi-cubical parabola, because see, parabola is of the form, if you want, y is equal to constant in x squared. Okay, but this will become this new pink curve, which is the evolute of the parabola, that will be of the form y is equal to constant into x to the power of 3 by 2. It's semi-cubical. It's x power 3 is cubical. X power 3 by 2 is semi-cubical. Okay, so it's called a semi-cubic parabola. Okay, so here again, you can see that it's the center of curvature that is tracing the evolute. Okay, but okay, so all this is all right. But but I have a question for you. Is this still doesn't explain how that curve showed up? See, in this case, the evolute of the parabola is semi-cubical parabola, and you're just looking at the evolute. I gave it as a fact to you that the evolute is gotten by looking at the path traced by the centers of curvature. All right. So if I look at the asteroid, for example, I get this pink one, which is a double size asteroid rotated by 45 degrees. Then for a nephroid, I get half size nephroid rotated by 90 degrees. And in the case of the ellipse, of course, I get this asymmetrical asteroid. That's all right. But my question to you is the following. Why is this happening? See, this is happening by itself, that's one thing, but why does this happen? So look at this thing. Why is it? Now you know that the at least as I have told you, there is this red ellipse, okay, and then I draw these black normals, and then suddenly this blue colored asymmetrical asteroid shows up, okay, and I am telling you that of course these points on the asteroid, I told you it's the evolute moving. The evolute of the ellipse is moving and tracing these things. But still, why is that showing up? But the question is, why does that shape show up? Why is this shape showing up? See, for example, this is a limacon. In the case of the limacon, which is a red colored apple shaped thing with a loop inside, okay, if I draw all the normals, then there is this kidney shaped nephroid here that's showing up, okay, and it is true that blue thing is the nephroid is actually the the evolute of this red shaped thing, okay, which is a limacon. Why is that blue shaped thing showing up? Similarly, look at this sinusoid here. The red shaped sinusoid is giving this blue shaped curve. Of course, this blue shaped curve is it is at this point it is singular, and at this point also it is singular, okay, so it's in pieces. But the point is, why do these curves show up? why does it show up? Now I'll show you something related, okay, so that's a question you have to ask. So here's something that I'll show you. So for example, if you take a cup of coffee, okay, then on the cup of coffee you see this, you watch this, right? There's this nice thing. Why does that show up? Similarly, if you have a metal sheet like this, and shine a light on it, you get this. You would have seen this in so many contexts. Why does this show up? I mean, what is this, bright picture that you're getting? Where is this coming from? So here is a water glass with light shining across it. Why do you get these things? Okay. And for that matter, it's also connected to why a rainbow shows up. Okay. So something is happening here. Yes? Lines are passing through? What do you mean by focus of the curve?
For example, we have ellipse and circle. We have a focus that is defined, and all the lines which are drawn perpendicular to the ellipse. It will, after reflection, it will just pass through the focus.
No, are you taking
focus 1 or focus 2?
But see, ellipse has only two foci, no? Ellipse has only two foci.
So therefore, we are getting that asteroid.
No, but I don't understand. The two foci are only the 2 points along the major axis, right? But that's only 2 points. Why should you get that curve? See, it's only 2 points. Why should you get that curve? By the way, see, you have all done this, no? You use this lens formula, spherical lens, okay, and so do you know that there is a restriction about that formula? So if I take, so my question is that suppose I take so let me change the color so that it's easier. So suppose I take something like this, I take so this is part of this is sphere, spherical shape, okay, and let me draw this a little nice. Somehow it's hard to draw, okay, and suppose I take one, so this is a part of a sphere, and then either I take a portion of the sphere and spherical shell, and then I mirror, make it a mirror. So this shaded thing is the place where I have put the mirror coating. So the reflecting side is a concave side. Okay. Then you all know that there is a so-called there is an axis which is the diameter, and this is the this is the center, and this is f is 1. You write f is 1 r by 2, right? And then you write this as r, right? And you know that if you put a ray coming from parallel to the principal axis, will after reflection will go like this. Okay, so this is how the focus is defined, right? So if you put another ray also, you will get like this, right? And the same kind of thing you can do it for the lens, except that it will be on the other side, right? If you put a biconvex lens, for example. Okay. Now my question is that so is this picture correct? Yeah. So what happens? So you need it to be small aperture, as it is called. What is aperture? Aperture is actually the angle subtended by the piece of the mirror or lens you are considering at the center of curvature. So you see, if you take something like a small portion here, okay, then this will subtend a very small angle here at the center of curvature, this angle theta. Theta should be small. That is the meaning of aperture. Aperture is how wide an angle it is subtending at the center. All right, this aperture should be small. If the aperture is small, then this is correct. Because have you seen the derivations of these things? You should always look at the mathematical derivations. So if you see the derivation carefully, you will see that somewhere calculus is used, limiting processes are used, and you are using the fact that sine theta can be approximated to theta and cos theta can be approximated to 1 if theta is small. Okay, this is used. Without that, this is not correct. So for a big mirror, as I have drawn, the mirror that I have drawn is wide aperture. Okay, what do you think will happen if a ray from infinity comes and hits it? Huh? Yeah. So will you be? So there won't be any focus. So what will you get anything at all? No, I mean, suppose it's all coming in one direction, okay, will you see something? So you take, so look at these pictures, that's what I showed you. See, look at these pictures. This is exactly what is happening. You get this curve. See, here what is happening is that, these are all light rays, let us say, coming from the sun. Okay, more or less they are, sun is an object at infinity, more or less. So all rays are parallel. So these are parallel rays coming at an angle, and you are getting this. Okay, more generally, if you do this, on a coffee cup also you get this. Okay, I mean, even a tube light is enough. I mean, you just put a cup of coffee, you will see this. So how is this related to the focus? What is happening? Yeah. No, for small, my question is, how do you get that curve? Yeah.
So, like he said, the aperture is kind of larger in this case.
Yes.
So, when the light comes and it reflects off the surface, it doesn't exactly go to the focus, but it goes in an approximation. That's why we get the small bend there.
No,
inside.
but see, okay, if you say that, then only at the center I should get some lot of light, right? Why am I getting this, this kind of shape?
Yes, so that's because
three kind of shapes.
So that's because not that some of the rays may pass normally. It's not that all rays, go only a set number of rays, go parallel and then go through the approximation of the focus. Some of the rays may hit the surface in various orientations. That's where we get to.
No, but all the rays are coming parallel. That is for sure. See, when they hit the curved surface, you can take them as coming parallel. So there is no problem in the angle at which the rays are hitting the surface. There is no problem with that. They are all coming from a parallel source. You can take it like that. Okay. But the question is, why is it that you are getting this particular curve? So, okay, so there is something here. There is something mathematical here that is going on. Okay. So the mathematical. So there's something physical going on, and there's something mathematical going on. They are the same. Physically, what is happening is what is called. It is called a caustic. A caustic is formed. Okay. So to understand what a caustic is, the mathematical term is envelope. Okay. So you have the following idea. So let me explain. So the mathematics is the following. See, if you have a curve, okay, then what you can do is just look at this. You start drawing tangents at every point. Okay. You start drawing tangents at every point. Okay. And forget the curve. What shows up? Take a circle, okay, draw tangents at every point. You take a circle and simply draw tangents at every point. Oops, I'll draw it with some patience. Let me do it somewhat. I draw tangents at every point. Just let me do this. Oops. Okay. Draw tangents at every point. Then what you do is forget the curve. Okay, so let me carefully forget the curve. What do you see? You still see the curve. Even after I forgotten the curve, you see it. Okay. Similarly, look at this. This is my original curve. Okay. Then you draw all the tangents. Then you forget the curve. Do you still see the curve? So what is happening? So what is happening is, you see, you can reconstruct the curve from its family of tangents. And why you are able to see the curve is because if you think of these various lines, the tangent lines, okay, see, when will you see something? Only if, several things intersect at that point. Okay. If two lines intersect at a point, you will see only a point, and if you think that the point is dimensionless, you will not see anything. Okay. But to see something solid, you need nearby things which you can see. That means you need nearby things where many lines should come close. Okay. So what is happening is, when you take a curve and when you draw the tangents to it, the tangents come closest to the curve. Okay, and the point is that even if you forget the curve, the tangents, because they are closest to the curve, you will still see the curve. From the family of tangents, you can get back your curve. And to get a curve for which a given family of lines or curves is tangent is called an envelope. So what is happening is that the tangents to the, so let me write this. You see, tangents to curve will have the curve. Let me write it like this. Envelope of tangents to the curve is equal to the curve. So what is an envelope? An envelope is something that touches every member of a given family. So I start with a curve. From this curve, I get a new family. What is that family? It is a family of tangents. Now, for that family of tangents, what is the envelope? My curve itself. Because the envelope, by definition, is going to be something that is going to touch every member of the family. And something that touches every member of a family is what shows up. Because what is happening is, after all, why should this circle show up? See, that's the place where all these tangents are coalescing. Okay. Okay. So that's why it is showing up. All right. Yeah. Yeah. So the definition of an envelope is, suppose you have one family of curves. Okay. Then a new curve is called an envelope for the original family if that new curve touches this family at every point, a unique member of this family at every point. In particular, if you take an envelope of a family of lines, it's going to be a curve that is going to touch every member of the family of lines. It means that this family of lines is exactly the family of tangents to that curve, right? You understand? So it's a completely, and this can be understood using calculus, using partial differentiation. Okay, you can write this on all using calculus. So what the important thing is, when you simply blindly draw lines, okay, whatever shows up, that is actually the envelope of those lines. That's what shows up. So what is happening in this, in this mirror with large aperture? You know what is happening in the case of mirror with large aperture? So this is what is happening. See, if you take, you get this curve, okay, this kind of a curve you get. This is what you see on the teacup or whatever it is, all right. And what is happening is the following. See, if you take a small portion of the mirror here, okay, then you know what will happen is that after if you take parallel rays, after reflection they will come to a point here, okay. And if you take a small portion here, okay, then a small aperture, if you take after reflection they will come to a point here. Now as this small portion, and when you come to somewhere here, okay, you get this point. And you see, if this small portion keeps moving, okay, then this point is also moving. Okay, and so how do you get exactly this curve? The way you get it is, it's actually the envelope of the reflected rays. So what is going to happen is, so let me show you, this is the mirror, and this is the envelope of reflected rays. Okay, and so I'll show you a nice picture. So here's a picture somewhere that I have bookmarked, and that's what you are seeing. So you see, where is it? So not this. I wanted to show. Yeah, I think maybe it's here. So what this? I wanted the following picture.